All right. By the way, even though I'm providing link on Zoom and recordings, it still doesn't meet the requirements to be in the class. Not for personal requirements, the requirements for theory. So you have to. So far, I haven't checked any attendance for the lectures, but at some point I might have to use this tool that allows you to automatically check attendance using QR codes. Not sure how it works or whatever. They promised it is going to work automatically, and one day I missed that without one. So my apologies, but it's a requirement. All right, let us now go to the material of the lecture. Last time you remember there was some horror story with matrices and the systems AX dot equal to AX plus BU. And we somehow used at least 3 different types of problems, and we solved all of them. And the problems were how to make a system stable, right, with control. So let me just remind you. Let's look at the lecture slide on the displayed here. So you see equation 11. That is something that we, I believe, covered last time. Am I correct? Okay, I'm impressed you remember equations we covered. I'm not sure, but okay, equation 11 we did cover. Equation 11 is just our general form of our state space formulation. And then what I ask you is, we have a solution x star, right? X star is a solution for the system. And we want to make it stable. Of course, those of you who are accredited and a lot of you are will tell me, okay, what does it mean for x star to be a solution? The solution only makes sense if you give the initial conditions, and in this case, I'll simplify what U is, right? I mean, A and B replace U as they are defined, right? But what U is not defined. So it is again one of those abuses of notation which we unfortunately use here. What we mean is when we say X star is a solution, we mean that there exists some U star which when you substitute into the equation, then you have some initial condition for which x star will be a solution. Okay? So when they say x star is a solution for this equation, or means there exists some initial condition and the control that will make it a solution. Okay, good. Now, so x star is a solution, and what I want is for you to find the control u, control law that would make it stable. So what does it mean? Well, it means that at the very least, this control law is supposed to be such that x star is still a solution. If x star is no longer a solution, we need to talk about it is not clear if what kind of situation we have. So x star should be a solution. But also, all solutions from a slightly different initial conditions should converge to x star. That is the definition of asymptotic stability, right? Or they at least should not diverge from x star. That is the definition of stability in the sense of Lyapunov. Okay? How is it different? Well, first we let's see. First, what we did was we said let's find u star. And u star in this case we found it by solving the equation. Substituting x star into the equation and solving it for u. Equation 13. You see, I used just expressed u star, and it involves a invertible B matrix. B matrix doesn't have to be invertible, but if x star is a solution, it should provide this expression 13 with the pseudo inverse should provide exact solution to the equation. And you understand this concept, right? That even if the matrix is not invertible, there can exist an exact solution. That is clear. Let me just give you one example because this is it seems like an important concept. So if I can find markers. So for example, let's say you have a system that looks like 0, 1, 0, 0, times x equals to 2, 0. Does it have a solution? Please. Yeah, what is the solution? Like, give me at least one solution. 0, right? I'm not sure, is there any other solutions? Oh, give me another solution. 1. Okay. That is exactly what this whole conversation is all about. So let me elaborate on this. 0 with the solution, easy. Right? You multiply, it's going to provide the equality. This is also a solution. It is b because of x. X equal to 0 is in fact the smallest possible solution. Just to do this, we'll discuss this in details, but this is the smallest possible solution. But in terms of the model, when I say you have the smallest state, we know with one of the sum. Huh? So you have 2 bars here, of course, yeah, indeed. That will be a better solution. So the reason why we have more than one solution is because A is not invertible. If A was invertible, it would be by definition a map from infinite space to the output in space, and it would have an inverse, which would be a map from output to input, it would be 1 to 1 map. Right? You remember this one now, this idea of linear characters as a map. So, because this is not invertible, it doesn't provide 1 to 1 map. In fact, it provides to this output, there is an entire subspace from the input space that can be found. Okay? So all of the operators of the form as you call it out, all of the operators of this form, constant and true, will belong to this field. So it is not invertible. Doesn't mean that this equation can be solved, but we can see this one. So this is the whole point of trying to be explicit about about cylinders. Cylinders allows us to work with non-invertible matrices, but sometimes there is a solution, sometimes there isn't. Let me give you some output that cannot be given by this linear operator. Which one? 2, 1. So this output cannot be given. Is that correct? What is the value of x that gives the closest possible value to the output? The smallest value of x that gives the closest output. 0 and 1. Is that correct? No, it's not correct. 0. 0 gives the closest possible, but still there is a residual. What is the residual? What is the smallest possible residual? Residual is the residual is the difference. If you want output y and you have input x, the residual is the difference ax minus y. What is the residual? 0, 1. In this case, I think it would be minus 1, right? But it doesn't matter. Okay, so we plot the terminology and we go to y as a p. So this was the reason why last time I stressed this point about sorry there. Okay, just for everyone who is in the Zoom call, I'm not sure if we will be able to provide like good interaction. I think. Let me just quickly make sure that I use the correct microphone. Okay. So sorry for everyone in the Zoom call and for everyone who is going to watch on YouTube, because I think I used the microphone from the laptop, not this one. Great. Great. So this was the reason why I put so much emphasis on the equation number 13 and equation number 14. So what is equation number 14? It is exactly the norm of the residuals that I just drew on the blackboard, right?
Let me see if the quality improved. Oh, okay. So thank you for everyone in the Zoom call. You helped a whole lot. All right, so you can see that this question number 13 is supposed to be solved exactly. Now, now we solved for U star, and the next step, and this is a step that you're going to repeat again and again and again in all your derivations. So please, this is still a recap, but please pay attention. We introduce control error. Control error is a concept that allows us to go from any type of problem to LTI problem of stabilizing the origin, so stabilizing zero. When I say stabilizing zero, we'll see what I mean in just one slide. But this introduction of control error is extremely important. By the way, notice that I use x minus x star. You can use a different definition of control error, but it will change your signs, so be careful. Okay, control error introduces x minus x star. And that is basically the measure how far you are from your solution. Okay, and now what we do is we just subtract solution equations that we use to compute U star from our equation. And we get, as you see, x dot minus x dot star equal to ax minus ax star plus bu minus bu star. And that after you substitute E instead of difference in x's, you get equation number 17, right? And we substitute also, we use new control variable v, just for simplicity, and we get equation 17, exactly what we know how to work with, right? We know how to control this equation. We know how to define control law. How? Well, now it is at the top of the slide. It is very easy, actually. All you do is you define the control law as minus ke. You substitute it into your equation, and you get, let me write it. What? Pseudo inverse? Pseudo inverse is, if you want to find the pseudo inverse, we write it like this. It is a generalization of an inverse, but I don't think I can give a detailed explanation. So for today, for all who haven't self-study, we'll go into it maybe sometime. Yes.
Like, why do we have exactly when we substitute v, we substitute for k, e, and then in the case we substitute u, we substitute by minus k, x. Why so have like an additional multiplier, like plus some constant?
You are referring to equation is 19?
18.
18. Yeah. So let's explore equation 18, where it comes from. So we have, this is a very important issue, and please don't with even, think they got it. Just follow me and check that you got it exactly the way I explained. It's just a methodological thing that is very useful. Okay, so we got our equation, which looks like E dot equals to AE plus BV, okay? That's what we have. I propose to use V as minus KE. I propose to do it. You don't have to follow my proposal. I just propose to do it. There are perfectly legitimate control laws of different form. But remember that usually when you have this expression, you want to stabilize 0 point by origin. Your control law would be linear. You can try to do something else, but see if it stabilizes origin. Probably not. So your control law will be linear. This is only linear control that exists. You can define your variables differently, but it is only a form. If I wanted a fine control law, I would have added constant here, or I would have put brackets and added something here. Affine control laws can have different formats. But the idea is, here we want to stabilize origin, so we use linear control law. And after I substitute this guy into here, what I get is E dot equals to A E minus B K E. And after I get E out of the brackets, I get E dot equal to A minus B K E. And this guy would have to be stable or have negative real parts of the eigenvalues. And that is all. So this is as long as I have procedures use K such that this whole guy has negative real parts of eigenvalues, I'm good. And this can be done by the whole placement, for example. You will hear about it, or you already heard about it in your practice. Pole placement for us is more or less a function in Python. We're not studying in details on most lectures for sure. So there are algorithms to find a solution to this. So you can see that all we did here is we just found a way to get a k. Now, we still need to find u, right? We don't know what u is. And what is u? Well, we know what v is. V is u minus u star. So from this, you know what u is. U is v plus u star. And what v is? Well, v is minus ke. So we write it minus ke plus u star. But what is e? E is x minus x star. So you get u equals to u star minus k times x minus x star. And that is how you get your control law integration variables. That is the path you want to follow every time you have a solution. You can variate in this path, of course. Sometimes it is impossible to get to this equation instantly. You need to do some work, sure. But this is basically the idea. Questions?
So this is the most general substitution that we will use.
It's not the most general, but it is just a useful pipeline to arrive to where it is.
So it's just the easiest way.
I'm not saying it is easiest or will change away any qualifiers. I'm just saying it works. Okay. So I cannot claim that it is somehow better than other things or worse. You could just use it, and it will arrive as a result. So let's move on. We will see exactly what's going on with the generality here. So again, as last time we pointed out, there is a feedback part, feed-forward part. This we call feed-forward. This we call feedback. Arbitrary, completely arbitrary. Why we call it such? Well, because this guy does not depend on state. So this feed-forward, as in like don't require any information from the system to pull it off. This does require information from the state of the system. You can also be purist about it. You can say, no, this guy also can be partially calculated without information in the system. Then you can define your feed forward as, for example, u star plus k x star, and your feedback would be something like minus kx. But this is not this is not a convention by any means. This is not a convention either. There are no conventions, but there's no real reason to be curious about what you call feedback and feed-forward. Just get that meaning out of the context and don't argue with each other what you call what. The topic is very simple. The reason we use ideas of feed-forward is because it does not depend on the state. So this is why it is used in turn. The reason we use the terminology of feedback is because feedback is the only part which includes k. And k matrix is what you get from pole placement, or as we later will learn from k to r. So k matrix can be calculated independently from feed-forward. And those vectors don't need to be calculated. So basically what happens is you have two pieces of information, u star and k, feed-forward, feedback. In this case, it's just looking to one, but you still get k in feedback formulation. And feed-forward still only contains u star. They're independent. That's the reason why it calls them different names. But don't be caught up in this notation.
All right, good. Now, no questions, or move on. Now to the new material. So when you get your x star equals to x star of t, your solution, it's called trajectory tracking. Okay, so we want basically our system to track a trajectory. We assume that this trajectory is feasible, and by feasible I mean it is a solution. Do you understand where the words come from, right? So trajectory is just basically what your system should follow, right? Your evolution in time. It is a solution by definition, but solution somehow implies that we solved something, which we didn't. We just propose how we want our system to move, and then if it is possible to move this way, it is a feasible trajectory, and in other words, it is a solution. Okay, so let's solve for let's just stabilize the trajectory x equals to x star for the system, affine system. System with c, it's an equation with x dot equals to x plus b plus c. We will see how it goes. So first of all, let me try to just use slides for this. So first of all, we have this equation 21. What is this? I just substitute my solution into my system, and this is legitimate. How do I know that it is legitimate? Or sorry, wait from I forgot what I got. Sorry. How do I know that it is legitimate? Well, I know because it is a solution, right? Now, what can I do? I can subtract it from my original equation. It was equation 20 to get error dynamics exactly the way we had here. Is it clear that I can do this? I mean, x dot minus x dot star will give me e dot, right? Same with a, same with b, and c will just cancel after the subtraction, right? Good. I can in exactly the same way calculate u star. The only difference is now we have c here. So we solve equation 21 for u, and you basically get equation 23. You get x dot minus ax minus c this time, and should inverse it by b. I mean, we didn't do anything really different. It is exactly the same. Even though the problem was a degree more challenging, the steps are exactly the same. Let's see how it goes next. So next we, yeah, I mean, there is no next for this guy. This is pretty much a solution, right? I can repeat exactly the same steps I got on the blackboard, and that is how I get my control law, and that's how I get my K. So we basically arrived at the same formulations before, so we don't, we know how to deal with it now. That is the power, one second, that is the power of our approach. We don't have to learn, 20 different paths to arrive to the solution of 20 different problems. We just need to know how to massage a problem into a, formulations that we know how to deal with. And, equation 22 is what we know how to deal with. So we got our new problem, which was equation 20, into the problem form 22. Now we can solve it. So you see that was one example of the generality of the formulation. We just solved a different problem with the same thing. Yes, your question. The C from in the equation 20 is just a constant. In 21, it is the same constant because we just substituted x into the 20, and hence in 23, it is the same constant. Good. Now let us tackle yet one more problem: point-to-point control. What is point-to-point control? Well, I don't in point-to-point control, I don't provide you a solution. I just tell you the end point where I want you to converge. So I don't tell you, okay, here's your x star of t that you want that I want to stabilize. No, I just say here's x star, x desired, and I want you to approach this x desired and converge to it from any initial conditions. It's a different problem. For one thing, you cannot really differentiate x star here because you don't know it's it's not given you as a function of time. It's given you as a constant. All right. So my first proposition is to use control law in exactly the same form as before. Affine control law 24. Please see how equation 24 looks. Exactly the same as what is on the blackboard, right? So I just propose to use it. Notice different steps, right? Instead of telling you, let's write error dynamics, I say, let's use this form because I know it is going to be good. So that is one of the ways to attack those problems. You know that your solution should have this form, probably, from experience. Just propose to use it. If it doesn't work, sure, fix it. But let's start with the proposition. Good. Now, I substituted into our equation. I substituted into our, ax, x dot equals to ax plus bu. What do I get? I get equation 25, where you see minus sign in front of b, right? Minus bk x minus x dot plus bu. Does it make sense how I got 25? I want you to make sure that you're not lost in algebra or didn't fall asleep. That is also very important. Algebra somehow helps, with having very good dreams. So just make sure you don't sleep over this explanation. Is it clear how I got 25? Okay, good. Now, what do I do with it? Well, what I can do with it is, what I can do with it is I can say, okay, first of all, let's make this equation. It is now at the top of the slide, and substitute our x desired into it. What is the trick here? Well, the trick is we know that this should make sense at the point x star, right? This equation is the equation that governs the behavior of the system at every point. So it should also govern it at the point x star. So let us substitute this x star into the equation, right? So we substituted, you can see it is equation 26, and we see that in the brackets, there is x star minus x star. So it goes to 0. That is because obviously, when we approach the point x star exactly, we shouldn't really have any feedback. We shouldn't really act on the error. We just, we are perfectly happy. We don't need, to multiply error by matrix K. Matrix K, you can think about it, and feedback control in general, as something that acts on your error and it tries to minimize it. Okay, error is 0, so feedback is 0. Good. Now you get equation 27. And equation 27 is something we can solve for u star. And that's exactly what we do. We pseudo inverse b, and we get equation 28. Does this sound like a completely different process? I would argue that what I did is just did the same steps, but in different order. I proposed the form of the control law, substituted it into the original equation. Then I put in the solution. And notice that I knew that at the solution, x star dot is equal to 0 at the solution. Why? Why did x star dot have to be equal to 0 at the solution? Because we want to converge to the solution, and we don't want to go anywhere from the solution. If at the solution, x star dot would be equal to x star dot would be equal to something other than 0, we would go away from x star dot, right? And we want to stay there. X star dot has to be a node, basically. So the system should not go away from the node. Is that not clear? Yes, yes. Yeah.
We need to make it a fixed point, though. Or we need to find some such u star that would make it into a fixed point. But you were, more or less right. X star doesn't have to be a fixed point, of course, because you don't know what fixed points are before you choose your u. After you choose what u is equal to, you will know what your fixed points are. Fixed point is not a constant function. Fixed point of a equation is of a differential equation is such a state that produces zero derivatives. So if your equation is defined as x dot equals to fx, then such x that produce fx equal to 0 are fixed points. Point to point is, you should arrive at the fixed point, of course, but we need to make it into a fixed point. Yeah, you were thinking right. It's just syntactically it is a little bit challenging, but you were thinking exactly correctly. All right, so you see, I just did the same thing in different order, and now we have point-to-point control. And notice at the bottom of the slide there is a tiny explanation how to make, how to choose k. And where does it come from? Well, you basically substitute equation 20. Let me write this just for clarity.
So you have, let me write it here. We have equation x dot equals to ax minus bk x minus x star plus b u star, correct? Yeah, correct. So I substitute u star as equal to minus, this minus, yeah, minus b sub inverse a x star, right? I substitute equation number 28 into the equation at the top of the slide. What do I get? I get x star, x dot equal to ax minus bk x minus x star plus b times b sub inverse in this case should annihilate to identity. Why? Because this should provide a zero residual solution. If it didn't, so if it didn't, it wouldn't have to annihilate. But in this case, it provides. 1 second, I will take the question. So we multiply these bases, we should get here a x star. So with a minus sign. With a minus sign. And this you can see will lead us to the equation. Yeah, and we know basically that x dot star is equal to 0, as we discussed previously. So I can subtract x dot star from here without changing anything. We can subtract 0 from anything. And we get e dot, because x minus x star is e dot, right? Here, this minus this is ae. And this guy is just bk times e. So we get e dot equals to a minus bk times e, and that is how we design our feedback. Yes, if there are questions. Yeah.
In this case, if we have a zero error, we can say that b is invertible.
We have zero residual.
Yes.
It's not invertible, it is just zero residual.
But in case if a zero residual doesn't imply that b pseudo-inverse equals to b inverse.
No. So if b inverse doesn't even exist in the first place in general case. So you cannot equate pseudo inverse to inverse if b is not invertible. If it is invertible, they always equal.
But why b?
So this argument, I would prefer not to do it without preparation because it's not clear to me how to deliver this argument. But the argument goes theoretically as follows. I would say, okay, I have an equation. Let's just say I have equation ax minus equals to y. Let's, for everyone, what I'm talking about is y, b, and b inverse collapse into identity here. So I have this equation, okay? And I know for a fact that it has exact solution. I know for a fact that it has x, such that ax equal to y, but a is not vertical. Okay, so I can write x equal to a sub inverse y. Now, what will happen if I multiply by a on both sides? We get ax here, a here, and I know for a fact that again I can just rewrite this as ax equal to y without any change in generality. So you see, it is not a statement about something deep about how sub inverses work. This is just a statement of if actually x can be found as sub inverse a times y, then I can multiply both sides by a and get a rigid equation. If there was if this was, let me just say, so the other case, if this, let me write this, plus, right? If this x would not, after multiplication, give me, if this would not give me a zero residual solution, so for what I mean is, what is the zero residual solution? That is, if ax minus y, x star minus y would not be equal to 0, then I cannot obviously multiply it by a and get my original equation. So you know, this would mean that ax star minus equals to a sub inverse y. We cannot do anything, anything with this. A times a sub inverse in this case does not collapse into anything. So it is not that b times b sub inverse in this case would collapse to identity. It is that b times b sub inverse times a x star collapse to x star, ax star. Understand? So it's just this formulation basically. If you know that the residual is 0, then it acts as a, for this particular vector input, it acts as the inverse. But as I said, I would prefer to tackle this problem with prep work and with graphical examples because this relatively abstract algebraic constants. So, yes?
But why have zero residual?
A residual of 0? If the residual is not 0 in the equation 28, then it means that our point to which we want to the system to converge cannot be made into a fixed point, so we cannot really stabilize it. If it would be made stabilizable, it would have a zero residual solution. Argument would go, in the same style of, in the same direction. You just try to reason. Let's say that you have a non-zero residual, but the point can be made with a fixed point, blah, 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 and you show that it is impossible. All right, but in general, it kind of comes back to the fact that if a linear system has a solution, exact solution, it will be found by least squares or pseudo-inverse. If it doesn't have a solution, then your pseudo-inverse will give you the smallest residual solution. Yes?
Why did we define u star like this way instead of defining it, for example, minus k x star?
Why do we define in 28? So equation 28 comes from the equation 27, which we solve for u.
Can we just define it as like negative x k x star?
No, equation 27 gives us exact relations, a relation for this problem. So we can try to find a different form to write this, but equation 28 as a solution for equation 27 is the only possible solution. You can add null space solutions to it, so you can find bigger u stars, which would do the same thing. That will go into weeks. Into this discussion. But basically, k has no place here, is my take. 1 second, let me just see. Okay, your questions, but we'll move on after that.
Okay, why don't we use left inverse in this case?
Is there any reason to use left inverse in this case?
Because we multiply in
But what is wrong with using pseudo-inverse?
Yeah, but instead pseudo-inverse.
Pseudo-inverse, I think, is perfectly clear for everyone. So, why introduce a new concept when you have one that is already perfectly clear? It's Occam razor.
It seems more logical.
I know the idea of left and right inverses kind of sounds appealing when you read about them, but we're only going to use something that is immediately useful in practice. Pseudo-inverse is immediately useful everywhere, so we're going to use it as long as we can. There is no drawbacks to using it here. So, all right, now we're moving on. Sorry about making everyone participate in the drawn-out discussion about inverses, but I promise we're going to do more of it. So please, if you feel not engaged, engage yourself. It's a very, very good discussion. My apologies for shocking you, but actually, linear algebra, the more you do it, the more you grow as a professional. You can decide to be a doctor and you still need linear algebra. So, and this is not a slight towards doctors. It is just a fact that algebra is useful everywhere. Okay, so this is actually your main benefit from the course as your skill set. Anyway, let's move on. And here you will find answers to some of the questions that were asked during the class. The questions that were asked were, what if we have a different form of feedback control? So I'm not sure who asked it when it was asked, but I think it was asked today, right? What if we have a different form of feedback control? Maybe I'm just imagining things because it's like such an obvious question. Equation 29 suggests a different form of control law. Please, everyone, look at the equation 29. What is the difference? It is for a system given at the first line on the slide. Let me see if I can use a clicker. I'm not sure if I can, but anyway, you get what I mean, right? At the top of the slide, there is a linear system. So what is the difference again? No X star. Yeah. No X star in the formulation. So can we even do anything about it? I mean, first of all, point is, someone comes to you and tells you, this is my control law, give me U star and give me X. And you can tell them, excuse me, but control law is supposed to be K times X minus X star. And they will tell you, excuse me, I will have an appointment with a different control engineer who does what I ask them. So, sometimes you just have to work in the framework of other people, right? And it is not a bad thing. Actually, your skill set is versatile enough to work with any formulation of control law. And you shouldn't be afraid of it. So instead of telling them reformulate your control law, we just use what they give us. So what is the approach here? Well, the approach is same as before when we were given control law. Last time I proposed to use the control law like a fixed structure. And next step was what? Substitute it, right? So I substituted again, give equation 30. I'm not sure, you probably cannot see it, so let me write it on the blackboard. Can you see it? No, so I'll write it on the blackboard. So my equation has the form x star equals to ax plus b, and my control has the form x minus kx plus u star, right? Oh, sorry, not x, u, of course. Let me use this one. U equals to minus kx. I substitute this guy into here, and what I get is x dot equals to ax plus minus
minus b times k times x plus b u star. That's equation number 30. Okay, so this is the next step. And what we can do is now do exactly the same as before. What I ask you here is to stabilize point x star, so point-to-point control. So I want point x star to be stabilized. Stabilized means it's supposed to be a node or a fixed point, and you have to find the control laws that makes it asymptotically stable. Okay, good. Now I substitute this guy here. I know, for example, that x dot star is equal to 0. Why? Because this fixed point, right? And so here we'll have 0. Here we'll have ax star minus b k x star plus b u star. Clear, right? Now, what we can do with this is just isolate x and isolate u. Let me even put u on the left-hand side. So let's say minus b u star is equal to a minus bk x star. You see what I did, right? And I can just solve now for u star. U star in this case is equal to pseudo-inverse minus sign b times a minus bk x star. Looks good? What is the difference from what we saw before? Some comment on what is the difference between this and what we saw before. Please press this.
I mean, the difference is obvious. The difference is that here we have a minus bk instead of just what we usually have a, right? Why? Why did it happen? Well, because last time, at the point, let me just quickly go back. I'm not sure if you will be able to see it, but I will quickly go back to the same problem statement we made. Equation 26, you can see it, right? Notice what is in the brackets, x star minus x star. It happened because at the equilibrium point, our control law is such that it has this bracket with x minus x star. I mean, it always has this bracket, but you substitute x star instead of x, at the equilibrium point you have 0 here. So the whole thing goes away. Now here, on the other hand, in this pure state feedback form, what you have is, you know, at the equilibrium point, you don't have any brackets. You just have x in front of k. So you basically your system behaves as if it is a new, you know, dynamical system. And your new a is just a minus bk, and that's it. Your new b is the same old b as before, but your new a, new state matrix, is a minus bk. So that is the whole story here. It's actually pretty straightforward. There's nothing strange going on here. Any questions? Yes?
So there are just two ways to find the control for the system?
I mean, you can define it in any way you want. I just proposed two very straightforward ways to define it, but a choice of variables, names, and the way you can split your control between different variables is probably almost infinite. But the procedure, as you can see, is very robust. It deals with any formulation. No more questions. Okay. Just to continue, what you do next is, you can see now on the slide, you have this, you know, you have the solution, u star equals to minus b pseudo inverse, etc. And no, it is indeed different from before. Now, okay, this is it for the lecture on different control forms. We probably have still time. Let me check. How much time do we have? Half an hour, right? All right, so we will start next lecture because this took like more than expected. So we'll start next lecture just so we can, be a little bit ahead. But we'll make like 5-minute break. Please don't go away. Just, if we start to go away, it will turn to 15-minute break. It's not going to be great. 5-minute break, and we start a next lecture. Okay.
Вот мы сейчас на протяжении 5 лекций изучаем, как сделать систему стабильной, в смысле там Липунова, асимптотика. То есть по факту как бы мы одну теорему как бы вот знаем, мы используем определение, а мы будем еще вводить там определение, новую теорию брать.
Конечно, конечно. Но эта теорема, которая на ней основана целая научная теория устойчивости. То есть то, что называется теоремой, для многих людей это не только предмет, это еще и вся их профессия. И большая часть инженерии основана тоже на этой теории. Масштабы того, что мы изучаем, их не недооценивать. Разнообразие будет, не переживайте.
Можно? В общем, бывают такие случаи, когда, допустим, вместо линейной зависимости между u и x мы используем замену, интересно, может x квадрат, может экспонент.
Да, нелинейное управление используется сплошь и рядом. Мы концентрируемся специально на линейном управлении, потому что оно используется намного чаще.
Все-таки бывают такие случаи?
Конечно, нелинейное управление сплошь и рядом используется. Может быть, я приведу примеры в конце курса. Сейчас нам рационально используют наше время для изучения линейного управления.
Можете дать какой-то пример, когда можем использовать нелинейное?
На самом деле, почти всегда, когда вы работаете с нелинейной системой, вы приходите к линейному управлению. Так или иначе. Я, может, приведу примеры на лекциях. Это не то, что может дать закон. Но фитформа, например, вычисляется из нелинейных управлений как нелинейные функции. Постройте для себя любое дифференциальное уравнение нелинейное и посчитайте u, которое приведет его к фикс-поинту.
Ну, как решать дифференциальное уравнение нелинейное, мы еще не изучали.
Его не нужно решать, вам нужно просто получить для этого уравнения фикс-поинт, то есть 0 в правой части. Попробуйте просто для системы уравнений первого порядка.
Понятно. Все.
us begin.
Let us start. Okay, so the topic for the next lecture is, next 20 minutes, I guess, is discrete systems. You probably already understand the idea of discrete system, right? Like the idea of discreteness, at least in some word, in some sense. I'm not sure what was your introduction to the word discrete, but for us, the idea of discreteness has to do with discreteness in terms of time. Okay. What does it mean, discreteness in terms of time? Well, it means that the system exists on a certain time stamps. Okay, so we say often that computers are discrete or numerical. We sometimes say, right? That means that instead of using signals which are, how should I put it, which are continuous in time, they use signals which are discretized, so they exist on certain timestamps. For example, your music is discretized at certain bit rate, right? And that means that with certain amount, there is sort of the amount of information for every second. It is not stored as a, what I'm saying right now is more philosophical than concrete. Of course, the music is compressed after discretization, so it's not how it is stored. But basically, the idea is you're not storing continuous values. You are storing the discrete values of your sound wave. Okay, so this is discretization. This is not the only thing that happens in numerical world. There is also quantization. Quantization means that your values cannot be stored with infinite precision. They are stored, in fact, with a finite precision. For example, integers are stored up to integer value. Reals stored up to what, I don't remember, 4 bytes can hold, or 8 bytes, depending on your system. There is a double precision, etc. But basically, your numbers are quantized. Not only numbers have to be quantized. For example, your variables or your signals can be quantized. Your sensors can produce outputs which are quantized. So, how should I put it? Let's say it can only measure 1/10 of a degree, your sensor, angle sensor. Things are quantized, but don't mix it with discreteness. Discreteness just refers to the fact that your values arrive on at certain points of time. So it's not the same as saying, discreteness is the way signal signs the computer. That's incorrect. Discreteness doesn't have to do with computer, and doesn't involve quantization. Okay, great. So discrete dynamics. Let us just see what I mean concretely. So equation number 1 here is a discrete dynamical system. We'll go to how we obtain it in a bit, but for now, just consider it as a given. I just give you this discrete dynamic equation number 1. What does it tell you? Someone?
Recursive dependency.
Yeah, it is you can say it is a recursive definition of X in a sense. But how exactly do you simulate it? Let's just ask it this way.
Using series, like sequence.
Yeah, you have your current X, you can find next X just by substituting it here, right? So you don't have to solve it in the sense as you solve differential equations. You don't have to try to formulate it in terms of exponentials or whatever. this is already a recipe for a solution. So sounds very easy, right? At least solving those equations requires only algebra. Doesn't require any integrals or whatever. That sounds very good. Now, the control law for a discrete system would also look, for example, the way I presented it here, very familiar. See this equation at the bottom of the slides. Here I used, again, what we call pure feedback. I mean, I didn't introduce X star, but doesn't matter. We can introduce it, of course. The point of this expression is that there is no difference for the control. You just do it the same way as before. Your system is very different, but your control is kind of the same. Okay, so no derivatives, very easy to simulate. Now, let us discuss stability of this thing. I guess let me try to talk through the derivation on the slide. So we do it exactly the same way as before. I cannot really talk through it because part of it is obscured. But okay, let me at least write it on the blackboard.
So my equation is x sub I plus 1 is equal to a times x sub I. Okay? And I want to discuss stability. What is stability? Stability for this system is convergence to 0. Basically, I want to find if it converges to 0 from any initial condition or not. My next step is to make eigendecomposition of A matrix. I assume that it exists. It doesn't have to exist, of course, right? But I assume it exists. A equals to V. I use V inverse times D times V, where D is the diagonal matrix with eigenvalues in the diagonal. If eigendecomposition didn't exist, I could always use something like complex eigenvalue decomposition, where I would have unitary matrices here. They would just be complex valued. But for us, it is just important to see where the derivation goes. You can repeat it all for complex eigenvalues on your own. Or maybe it is even on the slides. Okay, so I get x sub I plus 1 equals to V to the power of minus 1 times D times V times xi. Just substitute. And then I multiply everything by y. Why do I do this? I want to get rid of this guy, of this inverse. So I multiply everything by y. I can do it also because y is invertible matrix, as you can clearly see from this expression. Since y is invertible, I can do this. V is invertible. V is invertible. Okay. So far, so good. Now I denote a new variable. New variable will be called z, which will be equal to v times x sub I. And the new variable terms we have z sub I plus 1 is equal to z sub times x sub I. This is a diagonal matrix. So this whole equation becomes a system of equations where each equation has a form, some first value of z sub I plus 1 is equal to d, first on the diagonal times z 1 sub I. So you can see how it all evolves, right?
You see how it all evolves. Can someone tell me what d should be equal to in order for this equation to converge to 0? D is a constant here.
Negative.
Should be negative. If let's say d is minus 1, then and let's say that z is equal to 1, then it will oscillate between 1 and minus 1. If it is 0, it will converge in one step. But is it the only value that is appropriate? Between 0 and 1? okay, it will definitely converge for, let's say, 1/2, right? It would be divided in half on each step and will converge. But what about minus 1/2? It will also converge. It would just oscillate between, it would converge not in this fashion, but in this fashion, right? You understand that any d which by absolute value is less than 1 will make the whole thing converge to 0. Is that clear? That is a profoundly different thing from continuous systems. There we talked about real parts of the eigenvalue. Here we talk about absolute value of the eigenvalues. And indeed, we are going to talk the exact same way about complex eigenvalues. What we care about is the absolute value of them. So on the next slide, we have criteria. The criteria, which you can see only half of, unfortunately, says that for the system x sub I plus 1 equals to ax, each eigenvalue should be, by absolute value, less than or equal to 1 for the system to be stable, and strictly less than 1 for it to be asymptotically stable. Does it make sense? So by this argument, this is a stability criteria. Notice that actually we have now two criteria, one for continuous systems, one for discrete systems. Sounds like a big deal, but it's not really. It's easy to remember. And we can see how we derived it. If you're not sure, just rederive the whole criteria on your own. It is very fast. You saw how I did it. So, good. Now we have one more tool in our tool set. Now, how do we get those systems? Well, first approach is to discuss discretization. So let me try to write it.
Discretization. Let's say we have our familiar equation with differential equation, x dot equals to ax. Okay? X dot equals to ax. And we want this equation to be represented in some discretized form. What do we mean? Well, x can be represented approximately as x on the next time step minus x on the current time step divided by the time step. Does it make sense? Okay. Why does it make sense? Did you have it in one of your classes, or it is just a numerical way of finding the derivative? It looks like a definition of the derivative. That's why it makes sense, right? Oh, cool. This is also a numerical differentiation. So if you thought, how do I differentiate a function numerically? You do this way. For example, that is the simplest way to define the derivative. There are other ways to find the derivative. Let me show you. X dot can be also approximated as xi minus xi minus 1 divided by dt. Sounds like almost the same, but it's slightly different. I'm not sure if you have something more interesting in the slides. If we don't have if our function is not discretized yet, we can also do something like this. We can say x dot is equal to x of t plus 1/2 delta t minus x of, let me write it again, but x dot equals to x of t plus 1/2 delta t minus x of t minus 1/2 delta t divided by delta t. You can do this. This would be centered, right? You can do a lot of stuff. Actually, there are entire theorems and branches of mathematics which talk specifically about how to make this thing as precise as possible. So if you want to find your derivative numerically, you can go to the branch of mathematics. But let's focus on this for a while. So let's focus on this, and let's substitute into our equation here. So we will say that x sub I plus 1 minus x sub I divided by 1 over dt is equal to a x sub I. Now let me try to isolate this guy, x sub I plus 1. What I will get, I will first multiply everything by dt. dt is non-zero, obviously, so you can multiply. You will have x sub I plus 1 minus x sub I equal to a x I dt. Good. Now I just transfer this guy here. I will just do it this one. And now I want to write it in the form that is resembling this guy. So just take it out of the brackets. And my final form of the equation is x sub I plus 1 equals to dta plus I, in this case, times x sub I. This should make a whole lot of sense, at least it does to me. Let's just look into this equation. So first let's say that x sub I is exactly the same as x sub I plus 1 is exactly the same as x sub I because of the identity, except it changes a little bit. It changes a little bit by influence of matrix A. But how much does it influence? Well, the influence is checked by the time step. That is how we complete it. So,
and this is the derivation that we are going to, to be able to use. Now, unfortunately, the blackboard is unusable. So basically, when we have a time function, we can introduce those time steps, delta t, okay? You can introduce time steps, delta t, and you can evaluate the function at the step 0, step delta t, step 2 delta t, step 3 delta t, etc. And you can just call your states at those moments as state number 1, state number 2, state number 3, etc. That is all. So basically, you can, instead of saying you have a state as a function of t, you have a state as a function of the number, like state number 1, state number 2. Okay, that's all you need to do. And then you use this thing to get rid of your derivatives. And you get your discretization. Okay. So that is pretty much it. Let me just give you one more notion. And that notion is this notion is what if you try to do this step differently? Let me write it. What if you decided to do this step differently? Notice what I did here. I proposed to write it not in terms of the current state, but in terms of the following state. You cannot really tell me that I cannot do this. Why? Because basically it just depends on the choice of discretization. So if I discretize forward, I would have xi here. If I discretize backwards, I would have xi plus 1 here. Or if you want, I can rewrite all of this in terms of xi here and xi minus 1 here. The same thing. So notice what happened here. My derivative depends on the x in the future, not current x. Sounds absurd, but actually just a choice of discretization. Now, how will it make it different? Well, it will make it different in the sense that now when I collect my x sub I, what I have is x sub I plus 1 here, minus xi equals to delta t times a times x sub I plus 1. I put this guy here, and I get identity minus delta t times a multiply x sub I plus 1 equals to
xi. And now all I need is to pseudo-inverse this matrix. So I pseudo-inverse this matrix, and I inverse this matrix. If I cannot invert this matrix, this problem makes no sense. So it means that the future cannot be found. Or it means that there can exist simultaneous solutions. So it has to be invertible. Otherwise, your problem makes no sense. That is a nice thing to be able to say, right? It's like it can be not invertible, but then you just discard the problem. Okay, so x sub I plus 1 is equal to I minus delta t a inverse times x sub I. Okay, and it has to be invertible, by the way, for all x's in this formulation, because all x's are accessible. So it's not even a pseudo-inverse, it's the exact inverse. Okay. You can see it is also the same thing as before. You can just call this guy your UA, like A bar, and you arrive back at the latitude where we have degrees. But notice your discretization choices matter, and you need to be explicit about them. And this discretization is, I would call it backwards discretization. It is similar to backwards Euler method or implicit Euler. Maybe you heard about it. It is an integration scheme
which is famously stable for differential equations which are stiff, as we call them. So some differential equations where eigenvalues are very small and very big at the same time. So some of eigenvalue is tiny, some eigenvalue is huge. They're called stiff. It is hard to deal with them. You can use backward schemes in integration to deal with them. Discretization, I'm not sure if it would help, but they're legitimate choices, is what I mean. So, but there's a question in the chat. Okay. Right. So let us move on. So as I said, we can go now from this formulation to our discrete formulation. One more detail. Let me write one more detail. This is all good, but we still need to do something about the matrix. So let me write it here explicitly. Let's say we have A sub I, x sub I plus 1 minus x sub I divided by dt equal to AXI plus BQI. And multiplied by t, collected terms, I get x sub I plus 1 equals to A delta t plus I, here, sub I, x sub I, plus delta t B times U sub I. You can see that this guy is effectively my UA matrix, A bar. And this guy is my UB matrix, B bar. Notice that B also is affected. And of course it is affected, right? The effect of U will be measured by not B matrix, but also B matrix in the time that it acts. So by delta T. Should make perfect sense, I think. So notice that if you want to discretize, you take into account your delta T times that. And now we know how to construct our discrete systems. Why do we want discrete systems? Well, this is something that is hard to argue with our current tool sets, but essentially, first of all, real systems act like discrete systems when you implement control laws, because your control laws are discretized naturally by the frequency of your physical electronics, okay? So your electronics usually acts discretely. Your computers act discretely. So your systems at the end act like discrete systems. It is very easy to discretize your dynamics, but your control law is effectively cannot be made continuous. So going to discrete is easy, going to continuous is actually impossible. So real systems act as discrete systems. That is the first reason to like them. Second reason, you see no dots, so very easy to analyze, very easy to model. Of course, the discretization is actually imprecise, so your models are not going to be very precise either, but it is easy to work with them. That is the main reasons as DevOps name. A lot of the algorithms are specifically designed for discrete systems, and you cannot really make them continuous. For example, I'm not sure, maybe we'll have one of this, at the end, one class where we just dive into something very complicated. Maybe not, we'll see. But any really complicated method which allows you to work with the array of real systems would basically require discretization, because you want to guarantee something on each time step, rather than guaranteeing some abstract things like such as stability at convergence to solution at infinity. So you want to concretely say, in that step number 1, I will be here. That is easy to do with discrete systems, much more difficult with continuous ones. So in practice, they are very useful. But the tools for controlling them, you can already see are going to be more or less the same. So your A minus BK has to have eigenvalues, which are what? No. Less than 1. Yeah. So if you know how to do pole placement or whatever for continuous systems, just do the same for discrete systems, except ask for different eigenvalues. That is all. And so you see your tool set, which seemed very narrow, actually works for a new set of problems without any change. And that is a theme for linear systems. You can often generalize. So just more comments on notation. This is called zero order hold. Why? Well, it is easy to explain on the picture, but we cannot see the picture. That's very unfortunate. Let me try to draw the picture.
Make sense. So this discretization basically, what it says is that your x dot acts as a piecewise continuous function. So what you say is your x dot here, it acts as something that has the same value over the interval. Okay? And you compute it, when you multiply it by dt, you basically try to compute the area or under this curve, and that is like pretty much the whole story. So you say, okay, we have a derivative, which is x dot, which is the same during this whole period of time. And how we are going to discretize it this way, how we are going to compute x sub I plus 1, well, as an area under the curve. Stuff like that. So this is the story why it is 0 order hold. 0 because it doesn't change. You can also do a first order hold. So let's say your actual x dot. Let's say your actual x dot is has this form. You can say my x dot on each time step is a linear function. Okay? And you can try to compute your derivatives in such a way that it will be true. So that the next x sub I will be given as integral under this linear curve. It will depend on the x sub I basically. So your x is here. Your x sub I plus 1 is here. So your x sub I plus 1 would somehow depend on this whole curve. It's not trivial to predict. Like, as you can see, we are going into some strange territory where in order to find derivative, we would need to know the result of the integration, but we can do try to do something like this using algebra. Basically, the point is, instead of assuming your derivatives the same the whole time, you assume that it changes. That is at least my take. First of all, I never seen it used in practice, so I'm just giving you the general idea, but no one uses it. And the reason is because you can do exact discretization. Like, this is not exact. This is not exact. they have errors. But you can do exact discretization. What is exact discretization? Well, exact discretization is when you can simulate your system, your discrete system, and at the point of times where discretization happens, so at the point times x sub 1, sub 2, sub 3, sub 4, you get the exact same results of your simulation as you would if you solved your dynamics exactly. Okay?
So that would be exact discretization. And exact discretization is covered completely by the sun, but let me try to write it down. I'm not sure if it will be easy for me to do, but let me try. So exact discretization is given by a formula.
The formula is A bar equals to E to the power of A times, let me see, delta T. I don't remember the formula, so I will have to look it up. And B bar is much more difficult to compute. It is equal to B times integral from 0 to what? From T0 to T0 plus delta T of E to the power A S ds. Let me make sure it's correct. Yep. So this is the formulas. So if you have your A and B matrices, you can compute A bar and E bar and B bar by here taking the matrix exponential. Sounds crazy, right? But you can just call the function Python. And B, you compute it as an integral over matrix exponential. This is crazy, but hopefully, you can always do it numerically, or if there's a function that doesn't. But it is possible to do it, of course. I mean, numerically, matrix exponential is the same as any other exponential, is perfectly evaluatable. Integral of any reasonable function is also possible to evaluate. So you will be able to do it. And if you're going to go from zero order hold, your next step is not first order hold usually, at least in my experience, but exact discretization. And this you only need to compute it once offline, so usually it's perfectly reasonable to use numerical methods. Well, this is a message. Discretization is not something that you're given by one formula. You can choose different ways to discretize your derivatives, and at the end of the day, you'll get either something close enough, or something very wrong, or maybe something exact. Up to you. You don't have to go for exact discretization every time. In fact, most of the time, people use zero order hold, even in academic papers. So. But be aware that you can do better. Yes? Your input function is also discrete. You can see it is U sub I. So, yeah, discrete. More questions? Was there? Yes. So S is, I'm not sure how we call it, integration variable. So you can see it is in the dt. So it is variable that changes from t0 to t0 plus delta t, and you integrate in accordance to this variable. And after integration, it will become something like delta t. So you integrate with respect to this variable, then you get integration limits, you substitute, and it goes away. So it doesn't have physical meaning, it is just there for integration. In a messy notation, I could have just put delta t here, but it would be a violation of mathematical notation, and people already complain about it, so I will try not to do it when I don't have to. All right, so that is the main point of what I wanted to say about discretization. I think we are both out of time and we completed this part. I'm very happy that we did. It means that we'll be free to have one extra lecture at the end of the semester. So, I mean, the number of lecture slots is fixed, and the faster we go through the materials, the more we cover. Thank you so much for coming.